You guys want to make an announcement or are you good? What's that? Okay. Okay, everyone. I'm going to just get started. How are you guys doing? Good? Okay. So I checked the room, and this class is not available tomorrow at 4 to 6. But it's available 6:30 till the end of the night. So people who want to take the makeup homeworks or makeup quiz tomorrow, are they available at 6:30 or after? Good. So how many of you want to take like any of the homeworks or quizzes tomorrow? The makeup ones. Okay. Like around 10-ish? Okay. So, but the room is available on Friday at 4 to 6. So everyone is able to take them any of the 2 days? Good. Okay, so I'm just gonna make a note here that makeup homeworks 1 to 3, and I guess I'll write makeup quiz 1. Whether Thursday 6:30 to 8:30 or Friday. And I made this policy to myself that I ask the students to talk questions in the class. So I realized that this is the only way that I can stop students from talking, because nothing else matters to them, I feel like, but nobody wants me to call on their names and ask a question in case they don't know the answer. So just let you know, if you have any questions at any point, just like raise your hand and I can answer your question. Okay, so any questions so far about this? Good? Okay, so as I mentioned, anything that I have in the slides are from your book unless I cite another website or book or anything else. So again, because like this, slide is really important, I'm going to continue having it till the point that all of you know what is the difference between a pure substance, mixture, element, compound, molecule, atom. So you sitting there, I don't know the name, so I'm just going to point at you. So you know that you were talking, right? The person behind you, yeah. Right? Can you tell me what is an element?
A substance that can be broken down into substances.
Exactly. So the person next to you, can you tell me what is a mixture?
A mixture is a compound of different substances that are not completely united as
Okay, so what is an alloy? Is it a mixture or element or compound? So why alloy is a compound? Can anyone tell me? It's an alloy. So what is a compound? So can you give me an example? What is it? Sugar? Yes, so sugar, if you consider each of the sugar molecules you can consider that to be a compound. So sugar is a pure substance, but it's made of, molecules. So here, as your friend mentioned, for instance, C6H12O6, glucose. And that is a really good example of a compound, yes. But, so you see that you have like carbon, hydrogen, and oxygen atoms attached together with each other with like chemical bonds, right? But what is an alloy? Do you know what is an alloy? Does anyone know what is an alloy? Yes?
It's actually a homogeneous mixture.
Yes, it's a homogeneous mixture, but what is it? Like, so it is a homogeneous mixture, but it's kind of like I tell you water is a compound, but I tell you what is water. You know what I mean? So what is the definition of alloy? Yes?
Isn't it when you melt two metals together?
Exactly. So we have like a combination of a mixture of two metals. So depending on what alloy we have, we can have like different alloys. Some alloys, they consist of zinc and copper. Some of the pots that you're using for cooking at home, they can be steel. They have a copper and zinc in them. It might be other elements. But they don't form, a chemical bond. They're not attached with a chemical bond. We just, like as your friend mentioned, we have like two metals, we mix them, we melted them, and then kind of mix them together. Okay? So that's why alloys are homogeneous mixture. They're mixture because you just simply added two metals together, mix them. It's homogeneous because if I give you a pot that is like steel, it's an alloy, you cannot tell me which part of it is zinc, which part is copper, or like depending on what, texture it has, or like which alloy it is, we cannot say, we cannot distinguish the metals. So it would be homogeneous mixture. Good? Any questions? So again, remember, elements are put together in a periodic table of elements. And can anyone tell me, last session I asked you to remember 3 metals. Can anyone tell me what were they? Yes?
Lithium, sodium, and potassium.
Exactly. And I asked you to remember these because when you remember these, and each time when I add like some other elements, in next chapters when you see like the, when I give you problems to solve and everything, it would be much easier. So last session, we talked about lithium, sodium, potassium. Here, this session, I'm going to ask you to remember rubidium, cesium, francium. So you have like rubidium, cesium, and francium. So remember these 3 as well. So these are in group 1A, right? Remember that if I want to highlight this, this is like the first group, and we said except hydrogen, the rest are metals. And do you remember what state hydrogen has? Is hydrogen metal? What is it? Exactly, it's a gas, right? So remember lithium, sodium, potassium, you learned that last session. This session I asked you to remember rubidium, cesium, francium, okay? And if I give you an element and I tell you that, okay, I have like gallium here. What is its row number? Exactly. You see that you go horizontally. If I can make this work. Okay. You go horizontally and then you read the number here, which is 4. Right? You see that 4 over there? That is the period number or row number. So the same element here, gallium. I asked you what is its group number? What is it? 3A, right? So this is how you read, rows or groups. If you look at each row, you're looking at the row or period, right? And if you look at like each group, you're looking at the group or family. And kind of like to remind you again, last session we talked about lithium, sodium, potassium. This session I asked you to remember rubidium, cesium, francium. Okay? So these are in group 1A, and all of the ones that I just mentioned, there are metals. But we have also hydrogen in group 1A, which is not a metal. It's a gas, and it's the lightest element. Any questions so far? Good. Can anyone locate like the rows and groups if I give you an element and periodic table? Can you all do that? Is this clear how we do that? Okay, if this is clear, can anyone tell me if I talk about krypton, this element here? what is its row number and group number?
Row 4 and then the group number 88.
Exactly. Or if I ask, like, phosphorus, what is its group and row number? Yes, so this is like how you determine, these three over there, here, right? And here, you see like 5A, right? So this would be group, that would be the row number. Any questions? So again, this is kind of like our alphabets, periodic table. If you have difficulties like locating the elements in periodic table, it would be difficult to understand the rest of the material. So make sure that you understand these.
So for on the bottom, like the bottom part, I don't know what you call it, how to pronounce it.
Lanthanides and
Yeah.
these one.
When you say like group number, how would you classify those? Would it be like directly what's like the CE, would that be under 5B?
So this is really good question. So these, groups here, lanthanides and actinides, they have like basically, their own groups here, and we kind of put them here in the periodic table. So there are like exceptions, so we don't treat them like the other elements, and we don't read them as we reading the other ones, and you don't have to worry about them in this course. So they are like in groups, in their rows 6 and 7, because they are like basically here, but they have like their own groups,
Okay.
lanthanides and actinides.
Okay.
But as I said, in this course, basically we're not doing anything with them. So you don't have to worry about them. We just learn later on in chapter 9, when we talk about like electron configurations and orbitals, that they have like f orbitals, and this is how we distinguish them. But except that, we don't do anything with them in this course. So you don't have to worry about them. But great question, thank you. Any other questions? Okay. Well, yes, of course. So we talked about, again, these are kind of a review of the previous lecture. So physical and chemical properties. Can anyone tell me what was a physical property? Or give me an example. Smell, exactly. What about color? What about odor? Appearance. So what is the definition? And you're welcome to just read from the board too. I just want everyone to, kind of remember this. Or like you hear the definition with some other words. What other, voice rather than myself. Can anyone tell me what is a physical property?
Properties that can be displayed without changing the composition.
Exactly. So if we have like the example that I gave you before, if something, if you see this black, right, the composition doesn't change while you see this color black, right? Or like the same thing with other physical properties. And I'm going to ask you this in the exam, which of the following is not a physical property? So you should know physical properties to distinguish between physical and chemical properties. So what is chemical property? Yes?
A chemical property is one that's on display without changing its composition.
Exactly. So if we have like, piece of wood and we're burning that, right, kind of like flammability, like some matter, they're like more flammable compared to the others, right? So if something is burning, it changes its composition, right? Or like, if like iron, converts to iron oxide, if it rusts, its composition changes. So we have like Fe, now it becomes like Fe2O3. It becomes like, it changes its composition. So for that matter, we call these chemical properties because, they change their compositions while they're displaying chemical properties. And examples are corrosiveness, flammability, acidity, and toxicity. Any questions? And again, yes?
Would conductivity also be a chemical property, or would that be physical?
Conductivity, great question. Let me write this down. Conductivity. So if you have like piece of wire, like metallic wire, for instance, copper, does it change its composition? It doesn't, right? So it would be like physical. Great question. Again, always ask yourself, that when we have the property, does it change the composition or not? If it changes the composition, it would be chemical. If it doesn't change the composition, it would be physical. Okay, and we talked about also physical change and chemical change. And you have like this slide here as well. Can anyone tell me what is a physical change? Anyone?
The matter changes its appearance, but not its composition.
Exactly. So remember always like phase change, right? Or kind of like any of the phase changes. If you have like water in liquid phase, can anyone tell me what is the composition of water or what is the chemical formula? Exactly. So when you have like water in gas phase, what is the chemical formula? Exactly, it doesn't change. It's the same substance, just in different phase, right? For that matter, all the phase changes are like physical changes. But what about chemical change? Can anyone tell me? Again, I just want, someone else. You hear someone else's voice too. It won't be just me talking the whole class. Can anyone tell me what is a chemical change?
It's when the matter changes the composition.
Exactly, right? For instance, if you have like piece of wood and then you burn it, you change the composition of wood, right? You see ashes, and part of it, converts to carbon dioxide, right? So it changes the composition. And one of the good examples would be burning. And in general, a chemical change results in totally new substances, right? Kind of like rusting of iron, that you have like iron, and then it changes to iron oxide. It's like new substance. But for physical change, you have water in liquid phase, for instance, in evaporation. Now you have like water in gas phase. So it would be like the same substance. Good? Any questions? Okay, and also we talked about work and energy, right? Can anyone tell me what was work? Can you have like a slide or like a picture here too that I borrowed from like the reference that I posted there? So what is work? Yes?
The result of force acting on distance.
Exactly, so if you exert force on an object and then you see a movement, we have done, or I have done work, right? But remember, if I like put some force on something and it doesn't move, I didn't do any work. So it's basically multiplication of force and distance, right? And this is like all we're going to talk about in this course regarding work, So if you take like physics course, there are like more examples, more problems, you talk about vectors, and all that. But here it's just like all we talk about. And we have like two components in our universe. One of them is matter, the other is energy. And you probably will see this in like true or false questions. That, matter is one of the two major components of our universe. The other major component is a pure substance. True or false?
False.
False, right? So remember, all the definitions, and I put everything on this slide, and also your study guides, and I post them, so you have things to study well for your exams. Okay. So can anyone tell me what was law of conservation of energy? Anyone? Yes?
Matter is neither created or destroyed.
Energy is neither created or destroyed, excuse me.
Yes, exactly. As your friend mentioned, not created nor destroyed. And here I've included like these pictures from like this website here to kind of demonstrate my point. So if you see mechanical energy, that's because the chemical energy of a fuel converted to mechanical energy. So we just don't see like movement out of nowhere, right? So this is what it means. Or if you have an apple, like the famous example, and it falls, it's because you see like kinetic energy, which is because of something or an object having velocity, right? That is kinetic energy. And again, we don't go talk about the formulas and all that, but just know that when you have kinetic energy, that's because of velocity. And this energy just didn't come out of nowhere. That was potential energy of this apple. And can anyone tell me, does anyone remember what was potential energy? Or at least in this example, that why apple has like potential energy?
It has nutrients.
What's that?
It has nutrients.
It has nutrients. Yes, it can be. Yes.
Gravity.
Gravity, yeah. So what you said is also true, because we said that potential energy can be because of composition, right? So all the composition of materials that are inside the apple, and in this example, the thing that is really obvious is also the elevation of apple. So potential energy can be because of composition, as your friend mentioned, or potential or the elevation, as your other friend mentioned. And all objects that have like elevation from Earth, they have like potential energy. Again, we're not going into much details and talk about like gravity and then how to convert these things. But the thing that I expect you all to know is that energy is conserved, So it converts from one form to the other, but it doesn't generate out of nowhere. So probably, I'll ask you in the exam, and I say, is the following statement true or false? When we see a car moving, that the energy has been generated, by itself or something like that. So that statement would be false, right? Because we have like chemical energy that has been converted to mechanical energy. Does that make sense what I'm saying? Questions? Good? Okay. Again, here, your book mentioned like different types of energy, and I also, try to find like some pictures in the internet, because I realized sometimes I just have like text, and as I said, I include all the text, so you study them for your exam, and you'll be prepared. But sometimes it just becomes like too much, text, so I just want to kind of like spice it up with having like kind of like pictures as well. So kinetic energy in general is the energy of movement. Objects have kinetic energy because they have velocity, because they move. Okay, so if this book is just, still here, it doesn't have a kinetic energy. But if I just move it, now it has kinetic energy. Does that make sense? Or if I drop it, when it's falling, its potential energy converts to kinetic energy. And potential energy is the energy associated with position or composition, right, that your friends mentioned. So here, again, we have like an example, that you have like, because of the composition of the, air inside the balloon, and it can also be other gases like helium, neon, depending on what you have here. But imagine we just have like air inside them. That has like potential energy, and it converts, if we just kind of like release this, what do you call this? The piece of like string or whatever, it just like, the balloon moves, right? So potential energy converts to kinetic energy. And here, if we are on top of a mountain, and whatever this guy has, I don't know, it's like a big egg or whatever. So this piece of stone or whatever it is, on top of a hill, it has elevation, right? So it has like potential energy, and when he like, drops it, it converts to kinetic energy. Again, energy is conserved, is converting from like one form to the other. Any questions so far? Yes?
Did you have kinetic energy first and then
Uh-huh.
falling off the tree and then rolling to the water?
Yes, I mean, depending on when you look at your experiment, technically you can have like, kinetic energy first and then be converted to potential energy, yes. So these examples that I gave, they were like, reverse, but you may also have something that is like moving and then it stops and then the energy would be stored in it. So yeah, that's totally possible. Great question. Okay, any other questions? Okay, so you have like some other types of energy as well. So electrical energy. So electrical energy is the energy associated with flow of electric charge, right? We have that, like in electricity or like batteries, right? And this is basically the movement of electrons that we're going to talk about them more as we progress with the course. But in general, if I tell you what does the following definition represents, energy associated with the flow of electric charge. So I guess it's kind of, obvious in a sense because electrical, it has like electric charge in it, right? And thermal energy, energy associated with the random motions of atoms or molecules in matter. And we also call thermal energy heat. And this is something really important. We're going to talk about it in the next slides too. That in general, all matter, their constituent atoms or molecules, they have, some sort of movement. Remember when we talked about solids or like liquids or like gases, we said all of them have like some sort of motion, right? So which one then, in which of the states of matter, atoms could freely move, or like molecules could freely move, or like more freely compared to the others? Gases, exactly, right? And then for solids, what about solids? They can vibrate or oscillate, right? What about liquids? Exactly. They are similar to solids in a sense that they have like some sort of structure, but they can, more freely move compared to solids. But they cannot freely move as much as gases. That's why they take the shape of the container they are in, right? So if I have like, water bottle, it just takes the shape of the container. My water bottle, the water molecules won't be all around this room, because of the interactions between molecules, water molecules. Okay, of atoms, right? Here we said, thermal energy is energy associated with random motions of atoms and molecules. So if I heat an object, the motions would be more, right? So because the motion is more, the temperature would be higher, the thermal energy would be higher. So now, again, I have like all the things here listed because I'm going to ask you in the exam. So here we kind of like talk about like different types of energy, and we should know that the total energy of a sample of matter is the sum of its kinetic energy, and we talked about this definition, energy associated with the matter's motion, and potential energy, the energy associated with position or composition, right? So these are kind of summary of what I just told you, but I wrote them down so you study them to do well in your exams and homeworks and so on and so forth. Electrical energy is the energy associated with the flow of electric charge, right? And thermal energy is energy associated with the random motions of atoms and molecules. The hotter an object, the more thermal energy it contains. Can anyone tell me why is that? Why when a substance is hotter, it has like, more thermal energy?
The atoms are moving faster.
Exactly. So remember that this thermal energy, is connected to the movement. The object would be, hotter. Does that make sense? And I'm going to ask you this in your exam for sure, because it's really important. And chemical systems contain chemical energy. And we talked about chemical energy, which is a form of potential energy associated with the positions of the particles that compose the chemical systems. For example, the molecules that compose gasoline contain a substantial amount of chemical energy. They are a bit like the water behind a dam. Burning the gasoline is analogous to releasing the water from the dam. The chemical energy present in the gasoline is released upon burning. And I'm kind of like reading this to kind of like study with you in a sense. Any questions? Good. Don't scare you. Okay. So now, and I think I have like, so I do with like this slide over here. Any questions so far? Everything's good? Okay. So in general, we have like different units of energy. Do you remember that when we were talking about mass, we had like different units? Can anyone tell me a unit of mass as an example? Pound, yes. Kilogram, yes. What else? Gram, right? So we have like different units. What about volume? Can anyone tell me a unit for volume? Milliliter, yes.
Centimeters cubed.
Exactly, centimeter cube. So we have like different units. And also we have like different units for energy. Can anyone tell me, is energy a basic unit or a derived unit? Derived unit, right? Because I told you what was energy, Energy was the ability to do work, and we have like different source of energy, but in general, work's definition was like when I exert force on something and it moves. So it would be force multiplied by distance, right? So even if you don't know the unit of force, you know the unit of distance, which is meter, and when you do dimensional analysis, which was using units to solve the problems, you know that, okay, meter multiplied by some other unit cannot be basic unit, because meter is basic unit itself. So that would be derived unit. Does that make sense? Kind of? Okay, so basic unit of energy in SI units is joule, which is named after, James Joule, who demonstrated the energy could be converted from one type to another as long as the total energy is conserved. Kind of like what we mentioned before. And these are kind of energy. So here again, it's the same thing that I just like wrote it in a text format. When discussing energy transfer, we often define the object of our study as the system is just like the same thing, that I just had in the other slide. Okay? So the system of a study, or like the object of the study, we call that system. Anything else would be surrounding, right? And here we have like two more definitions. We already talked about thermal energy, that the atoms and molecules that compose matter are in constant, random motion. So basically they have thermal energy, right? So we talked about that before. And we have two definitions, and in chapter 7, we're going to talk about these two terms in more detail. As of right now, I want you guys to know that we have like two types of reactions. So here, basically, I just asked you these two as of right now. In exothermic reaction, energy is released. In endothermic reaction, energy is absorbed. For now, you just know these two sentences. And in chapter 7, I talk in more detail about this. Does that seem good? Any questions? Okay, slide here. Through some slides that have pictures. Different units of energy. Joule, calorie, and we have like two different calories. One of them is like capital C, the other one is like, like a small letter C, and then kilowatt hour. Okay, so remember these different units. And again, each of them we can explain more and then talk in more details how we drive these, but I just need you to know that these are units of energy. So I asked you in the exam, that which of the following is not a unit of energy? And it tell you like joule, calorie, kilowatt hour, kilowatt. Which one? Kilowatt. That is the unit of power, not energy. Okay? So, and here you have like different conversion factors. So I may give you questions to use these conversion factors, but I don't require you to know the numbers. So you don't have to worry about knowing these numbers here. So I guess I wrote that here. You do not need to memorize the numbers, but you should be able to use them to solve problems. And next sessions, I'm going to give you some examples. I'll walk through some examples, and also I'll give you your SI Pass leader some questions to walk you through them. But as I said, just remember these are like units of type. Let me see. Okay, so before I talk about different units of energy, let's just have some pictures again. In general, in chemistry, in physics, in thermodynamics, in some other courses that you encounter or may encounter, we sometimes talk about systems. So system is whatever we are studying. So if I'm talking about burning of wood, right, the wood would be like my system, and then the oxygen or the air around it. Or if I'm talking about moving this book, the book would be my system. So in general, when discussing energy transfer, and it can be when we're talking about matter as well. But here your book, mostly talks about systems when we're talking about energy transfer. But technically, when you're dealing with matter, you can also consider systems. Does that make sense? So you may have a gallon of water here, and we're calculating the flow of water from the system or out of the system. We call that system too. So it can be both for matter and energy. But here your book talks about systems in the context of energy. We often define the object of our study, such as a flask in which a chemical reaction is occurring, as the system. The system then exchanges energy with its surrounding. So the thing that we are studying, we call that system. Anything else in the world, we call that surrounding. Right? So if I have a flask of water here and I'm studying that would be my system. The rest of the world would be my surrounding. But most of the time, if I'm here, probably, I don't know, a building far from UI, that's too far. So surrounding would be just this room, you know what I mean? But technically, anything else in the world would be my surrounding. And the thing that separates system from surrounding is the boundary. Does that make sense? And these things, we don't talk about any of these in much detail in this course, and it seems really easy. But if you have a thermodynamic course or more advanced courses, sometimes it's difficult to determine what is the system. Sometimes you have systems that they are moving, and then when you solve the problems, it would be hard to distinguish the system. But in this course, it would be really easy. So you don't have to worry about it much. But this is how we depict the system, and this is where I got this picture from. And we also, here, I talk about endothermic and exothermic momentarily, but at first I wanted to talk about systems and also kind of if we consider our system, the energy is going out of the system. The heat is going out of the system to the surrounding. We call that reactions exothermic reaction. And then I'll talk about enthalpy in the next chapter, so as of right now, you don't have to worry about it. But can anyone tell me an example of a chemical change that is exothermic, meaning that it releases energy to the surrounding? Yes?
That'd be like water when it reaches its boiling point, that energy is being released through steam.
So That's a thought-provoking, example, but is that a chemical change? That is a physical change. So right now we're talking about like chemical changes.
Oh, so with like sodium being dropped in water?
Yes, so if it releases energy, yes. Or like one other example can be burning, right? So if you have a piece of wood and then you burn it, when energy is released to the surrounding or environment, that would be like exothermic reaction, or the example that your friend gave, right? If you have like sodium that it releases energy to the surrounding, it would be exothermic reaction. And endothermic reaction is the opposite. Energy is being entered to the system from surrounding. Okay? So lots of absorption reactions would be like endothermic. For instance, if you have an ice pack and then you break the distance between them, you crack them, and that would be kind of like because absorption happens, and then you'll be having like endothermic reaction. But again, about like endothermic, exothermic is the material of chapter 7. So I'm going to talk in more details then and kind of like distinguish in different types of reaction. As of right now, I just want you to know that if energy goes out of the system, we'll be having exothermic reaction. If it comes to the system, that would be endothermic. Does that make sense? Any questions? Okay. We talked about temperature before, and here again I included that in this slide. The atoms and molecules that compose matter are in constant random motion. They contain thermal energy. So the temperature that you sense when you touch different objects, that temperature is because of motion of their particles, or like their molecules or atoms. So if you touch a pot that is hot, because the motion of the elements of that pot, or like atoms of that pot, is kind of like higher. They are like moving faster. They have more kinetic energy because they have like more thermal energy. Does that make sense? Any questions about that? Good. Okay, the temperature of a substance is a measure of its thermal energy. The hotter an object, the greater the random motion of the atoms and molecules that compose it, and the higher its temperature. We must be careful not to confuse temperature with heat. Okay? So the temperature of an object, we have like units of Kelvin or Celsius or like Fahrenheit, right? But heat is type of energy. The units are like joule, calorie, kilowatt hour. So don't confuse them. And again, you can do dimensional analysis. You can use units to guide you solve problems. So if you write the units, you see that the units are different. So you don't confuse temperature with work. Heat, which has units, I just shouted too much. I'm just kind of like out of breath. Anyway, and I kind of emphasize, again, I'm shouting because first of all, I just want to go through the materials, and also I want everyone to hear me well, and also because I'm recording the lecture. So I don't want to be any misunderstanding, that I'm like mad or kind of like I'm yelling, I just want everyone to hear me well. Anyway, heat, which has units of energy, is the transfer or exchange of thermal energy caused by a temperature difference. So if you have like a hot object and you put it here, the table becomes a little hot because there's temperature difference, and then you'll be having like exchange of energy, okay? But if you put like two things that they have like the same the same temperature, you won't be having flow of energy. Does that make sense? Okay, so I talked about this briefly, that we have like different temperature scales. The most familiar in United States is Fahrenheit, and the most conventional one, or the ones that usually scientists use, is like Celsius or like centigrade, right? And we have another scale, Kelvin, that avoids negative temperature. And the lowest temperature possible is 0 Kelvin. And I always ask this in the exams, and always students answer that wrong. Or like most of the time, 90% of the time, students get confused with that. So the lowest temperature possible is 0 Kelvin. So we cannot have like -1 Kelvin. That's not possible. And can anyone tell me what happens when we have like the lowest temperature possible? Why don't I have like -1 Kelvin? Why can't I just go lower? Yes?
The molecules stop moving.
Exactly. We said temperature is like a measurement of, see, the random motion of molecules or atoms, right? So when they completely stop, we have 0 Kelvin. So it cannot be lower than that. That's why we don't have like -2 Kelvin, because that doesn't make any sense. When molecules stop, it would be 0 Kelvin. Does that make sense? Okay. So that avoids negative temperature. So I give you in the exam and I say which one of the following sentences is not correct. We measure the substance and the temperature is like -2 Kelvin, and then I say -2 Fahrenheit and I say -2 centigrade. So you know -2 Kelvin does not exist. Okay? So you read these sentences, and I had like this issue last semester with the students that I post study guides and then they still answer some questions wrong, because you should read each sentence and make sure you understand it. If you have questions, just like email me and I'd be more happy to answer those. And absolute 0 is the temperature at which molecular motion virtually stops. There is no lower temperature, and that is like 0 Kelvin. And we can use these two conversion factors to convert, units. So we can convert Celsius to Kelvin with this formula and Fahrenheit to Celsius with this formula. And I go through some examples next session, so I make sure you understand this. But as of right now, know the formulas here. And I cannot go through the rest of the lecture, so let's do the attendance. And make sure to just complete it right now. And we have 3 minutes, so we should be good. And originally, I wanted to host your quiz 1, or rather quiz 2 today, but I want to include as much as material from chapter 4, because you're going to see chapter 4 in the exam. So I want you to have a sample to use, for your exam. So I'm going to post quiz 2 on Monday, or so I make sure that you have a sample for your exam. Does that make sense? Yes.
The website's not working.
Did anyone made it work? Okay, so let me just come to you then. Okay, I'll come to you guys. if you release an exam, you just send me a letter or something that I can schedule and make up for you.
And then my lab team said that there would be something I could do to make up the lab.
So if you can attend another lab that week,
I will be here.
so it would be just an excuse absence, let them know, because you can make up a lab the same week, but not afterwards, you know.
Yeah, good. Thank you.
Thank you.
I got an email from you earlier about a missing lab.
Uh-huh.
It's just that Kelsey said that I was missing.
So you're the one that you didn't register for the course?
Yeah, I only registered
I mean,
for last week.
okay, but where you going to the lab?
Yeah, I can go to the lab.
Okay, so you're all set, you know, he just mentioned that you didn't add the class yet, or the lab, I wasn't sure if you were going or not going, I just wanted to clarify, make
Oh,
sure that you didn't miss any lab.
No,
But you're all
I've
set.
been going to all the ones that have been
So
registered.
you're all set,
Oh, okay,
yeah,
sweet.
yeah, thank you, thank you.
Just quick questions for, so exothermic would be like a reactor.
Uh-huh.
And then endothermic would be like if you had a light bulb that was using that power to generate light.
Mm-hmm.
So that would be endothermic, correct? In a sense?
So.
So anything that kind of takes that energy and uses it
Uh-huh.
versus it creating its own energy.
So, I mean, light bulb is a little tricky because light bulb also gets really hot
Mm-hmm.
and then it releases
Releases,
energy,
yeah.
but it also, you know, it
Uses.
uses electrical energy, so it comes to the system. So that's why, you know, we mostly talk about like chemical reactions and then see that if we're burning something, we see heat being released, you know.
Yeah.
And in general, in all reactions, we should have like an activation energy. So meaning that in all reactions, we should give our reactants, basically the substances that react with each other,
Yeah.
a little amount of energy. And for some substances, it's just like the energy
So
is
you're
more.
always putting something in, even if it's a little bit, and you're getting
Exactly.
something out.
Even for like burning, you know, if we just have wood here by itself, and even if I put like gasoline in it, even like if I put oil or like
Yeah, it wouldn't go.
exactly, we need a spark, we need
Yeah.
like a little energy for it to start the reaction.
Mhm.
But in general, for the in a sense that which one is dominant. So for like burning, you know, that activation energy is lower than the amount of energy being released, you know. And when we progress with the course, you know, I'll tell you. I mean, I guess, you know, I don't. I mean, in chapter 7, I talk about this, you know, in briefly. That, you know, we have like some sort of energy diagram like
Oh, I
this, you know.
see, okay,
that,
as it loses fuel, it loses energy output.
Exactly, that we
Okay.
have like this, you know, activation energy
So would
here.
that technically be like potential energy that you haven't generated yet, like when you're burning wood? It has potential energy inside of it?
Yes, so wood has like potential energy
Mhm.
inside of it,
Okay.
so, which is due to its composition.
Yeah.
So sometimes you have like potential energy because of like elevation, like the apple example,
Yeah.
or like, you know, this book has like elevation.
Well,
elevation.
then wouldn't the apple technically, even, let's say it falls and hits the ground, I walk over and I pick it up and I eat it, wouldn't that still be transfer of potential energy from the energy like the calories
Uh-huh.
inside of the apple to my body that I use for motion?
Exactly.
And then, so my question is if they say that energy can't be created or destroyed, how does the energy that I use for motion
Uh-huh.
generate energy transferred back into, like, I guess a system, like an external system of myself?
So for instance, you know, if I like move this object, you know,
Yeah,
I transferred the mechanical energy to it. Again, you know, it has like, you know, some sort of like, you know, it still has like elevation, so it's that potential energy. And also, it's kind of like, the energy would be conserved in it. You
Okay,
know?
yeah.
So it's kind of like, you know, the example that you gave. So even if you like do movement, you know, technically that energy won't, you know, won't be destroyed.
Mhm.
It would be like, you know, conserved in universe in some other form. Does that
like,
make sense?
okay, yeah, kind of. I was just wondering, so if there's always energy flowing, like, between objects, so like when I move, the air around me moves, generating energy to the air, I guess you could say?
Yeah, I guess you can say that.
Okay.
Yeah.
That's what I was wondering, because I was like thinking about the car and I was like, well, it just uses mechanical energy, like after it's transferred the energy, where does that energy that you got out of the movement of the car go?
Or like, one of the good examples is like thermal energy, that when the car moves, it has like, heat generated because of the tires.
Yeah,
And
on
then
the road.
or when I'm like standing here, when I move, technically it's kind of like the heat that is be generated, it's
Okay.
kind of like increases the energy of the particles, if you think about it.
Okay.
So, or the example of the air around you that you mentioned,
Mhm.
So basically it just doesn't disappear, it kind of like be conserved.
It goes to something else in
Yes, whether
whatever
it's
way.
like, exactly, whether it's
Okay.
like potential energy or like thermal energy, but it would be conserved, it's just not like disappearing, And sometimes it may seem like, or like even like law of conservation of matter, we burn something and it becomes ashes, or like it
even if you can't
changes.
see it, it changes.
Yes, so
Okay.
it's kind of like, I guess it's trickier with law of conservation of energy because, like the
You don't
examples that
see
you
it.
gave, yeah, it's kind of like what happened to it.
Yeah.
But, it's kind of like, because of the friction that we have, or like kind of like the example that I was giving, kind of like increasing the thermal energy or like temperature. So technically, it would be conserved, it becomes like potential energy of some other object, It's kind of like what, your friend was mentioning, that yes, velocity or like kinetic energy can also convert to potential energy. It's not like always the other way around.
Okay. And then for the last part, when you were talking about the heat, don't get the temperature and heat mixed up,